So some quick review where we left off. We've been talking about, we started out with the time dilation equation. We called this square root thing, if any of you go into upper level physics and you do what's called modern physics, which is what Einstein is a part of, nobody writes that square root thing. You may have noticed in physics we tend to abbreviate. We replace it with the letter gamma, and so we write it as T naught or T0 over gamma, or L0 times gamma. And we tried calculating where we started to notice time dilation. And we said, Alicia, even Earth around the sun, that's not going to affect your life. Well, once you start talking about particle accelerators or things like that, then it starts to make a difference. Then we talked about length contraction. I didn't prove this equation with you exactly, but I said it turns out objects that are moving appear shorter. So for objects that are moving, time slows down. For objects that are moving, their length contracts in the same direction that they're moving. And so I gave you I think I showed you kind of a graphic of the Earth looking really, really skinny, because if you were passing by in that direction, its height wouldn't change, but this would change. And that's what you would see if you had Superman eyes and you were moving near the speed of light. We said that L equals L0 times the gamma function times the square root thingy, where L was what we call the relativistic length, the shorter length. L0 was the original length at rest. And Hannah, that's how I've always remembered that one. So for time, I think time 0 stands for time on board the spaceship. But for L, I think the 0 stands for original length at rest. We've revisited the planetary travel, and we said one of the ways that we could explain why we measure 15.6 light years of distance from Earth, but when the spaceship travels that distance, it only measures a trip of 4.87 light years, is because as far as the spaceship is concerned, it's not moving. The universe is moving past it. And so it sees all the lengths of the universe contracted. And so, Hannah, it only gets 4.87 light years of distance versus 15.6 light years of distance. I was going to go over your forces test at the beginning of class. I'm into the lesson right now, but make sure I don't forget to go over your forces test at the end of the lesson, because I'm riffing. I've got too into this. That never happens. We paused here. Oh, I showed you the possible way to travel into the past by towing a wormhole near a black hole. Very far-fetched, but it doesn't, mathematically right now, there's nothing against it. Probably once we learn more physics, Jordan will find that you can't do it. Third one gets even stranger, but cooler. Einstein, I'm not going to prove this one, Einstein showed that as objects speed up, there's an increase in mass. This is governed by this equation. Sarah, it's the same as the time equation, except instead of T's, there's M's and M0s, where M0 is the original mass at rest. If you're at rest, what's your speed in meters per second exactly? So I think M0 stands for original mass at speed 0, whichever way you want to keep that straight. And M is the relativistic mass, and it is larger. As an object speeds up, its mass increases. You can write it with the Lorentz factor as M equals M0 over that funky gamma symbol. We said that gamma symbol was like a little fish doing a headstand, but a really skinny fish. So, suppose an object had a mass of 10 kilograms at rest, a bowling ball. What would its mass be if it was traveling at 2.5 times 10 to the 8th meters per second? Which mass is this asking me to find, M or M0? That's the part you'll need to kind of figure out. So read the question carefully and ask, is this asking me to find M0, the original mass at rest, or M, the relativistic mass? M, okay? So let's make a little M equals question mark. Let's see if we can just be bold, Xavier. Let's try going straight to plugging in stuff. So it's going to be M equals M0 over gamma. What's M0, the original mass at rest? 10? All over. Did I give you the speed as a percentage of the speed of light? Or did I give you the speed in meters per second? Okay, so unfortunately this time what do you see is not going to work, Shay. I'm actually going to have to go square root of 1 minus, and then in brackets, 2.5 times 10 to the 8th over 3 times 10 to the 8th squared. Please remember I did give you the speed of light on your green sheet in the relativity section. It's there. I really, really encourage all of you to try typing these in, because one of the things, this is plug and chug, but it's complicated plug and chug. You really need to know how to type these into your calculator. How would I do this one? I would probably go 2.5 times 10 to the 8th divided by 3, scientific notation button 8. I would get that decimal first inside the brackets. And then I would square that. 1 minus that. Square root of that, and then 10 divided by that. Did I make a mistake, or is it 18.1? 18.1? Okay. So this 10 kilogram mass at this speed would have a mass of 18.1 kilograms. In other words, if you're doing F equals what? If you're doing a force equation, you would use a mass of 18.1 at this speed. Let's go faster. 98% of the speed of light. Oh, this time I gave it to you as a percentage, which I think makes things a little easier. Donald, it's going to be M equals 10 divided by the square root of 1 minus 0.98 C over C, all squared. Donald, do you see? Do you see? Do you see? What do you see? Well, that's always nice. So I'll try typing this in one step now. It's going to be 10 divided by square root bracket 1 minus 0.98 squared. I think that's, if I wanted to type that in one step, how I would do it. Do you all get 50.3? So already we got 5 times heavier, a little bit more than 5 times heavier. And that's going to be kilograms. What about 99% the speed of light? You know, since I typed this in, I can probably just backspace and edit. It's going to be the square root of 1 minus 0.99 C over C, all squared. Do you see? Do you see? Do you see? Yeah, I can backspace and edit. I can change the 9.8 to a 9.9. 1% faster. Pretty big difference in mass. 20.8, well, 70.9, so over 20 kilograms more. Is that right? 70.9? I need to update D because they've made the Large Hadron Collider stronger. But back when I first typed up these notes, the Large Hadron Collider could get protons up to 1, 2, 3, 4, 5, 6, 7, 8 nines followed by a 1. So on your calculator where the 0.99 was, now try putting 8 nines followed by a 1 squared. 1, 2. What would the mass of this 10 kilogram object be at that speed? Ethan, what'd you get? because you're completely trying along after I said I encourage you all to follow along with your calculators. Right? Right. I got 74, wow. Did you get 74,500 kilograms? Yeah. What do you think the mass would be if you tried to go the speed of light? In fact, it's infinity. It shoots off to infinity. How much energy do you think it would take to get an object of infinite mass to the speed of light? Karen's eyebrow raised. I love that. You did the Mr. Spock single eyebrow raise. I wish I could do that. I've tried and practiced in front of a mirror to see if I could do the single eyebrow like Mr. Spock. I'm that much of a nerd. I can't. But what were you thinking? What did you say? Yeah. So he said infinite. This is why any object with mass can never get to light speed. To get there would require more energy than there is in the universe. There's a corollary to that. It means if you're traveling at light speed, you don't have mass. Photons, particles of light, have no mass. Okay? In 2015, the poster on the wall behind Ethan and Adam, a Canadian physicist and a couple other physicists, they shared the Nobel Prize because they were able to show that neutrinos have mass. Neutrinos are very, very tiny object. They're neutrally charged, which is why they're called neutrinos. Because, Hannah, they're neutrally charged, they don't interact with anything, but they're everywhere. Everybody hold your thumb out, look at your thumbnail. It's about 1 billion neutrinos going through there every second. They're going through you like crazy. They don't interact with anything. They almost never interact with anything because they're neutrally charged. You learned in Science 9, like charges repel, unlike charges attract, and all your ion chemistry stuff. Well, none of that works for neutrinos because they don't have a charge. I think I read that if you wanted to stop a neutrino, it would take something like 6 trillion light years thickness of lead, and that would stop a neutrino. Like, it's ridiculous. They're given off by stars, so the sun sends lots of neutrinos towards us. Turns out neutrinos have mass. It was thought that they did not. It was thought that neutrinos were similar or belonged to a similar class of particles as light. So here's the cool experiment that they did. You'll like this. We built a neutrino detector in the 70s. We calculated how many neutrinos were coming from the sun. We built a detector. They almost never interact, but every once in a while they do. And so if you wait long enough, you can detect a few of them, Hannah. And when we calculated how many we were detecting, we only found 1/3 as many as we were calculating. And so there was for about 15 years a big debate between, were the calculations wrong? They were checked and rechecked. No, they weren't. Was the detector wrong? Checked. No, it was working fine. And then they realized there's 3 types of neutrinos. The sun puts out one type of neutrino. I think they're tau neutrinos. And so the detector was only looking for tau neutrinos. Somebody said, what if between the sun and the earth, the neutrinos change into the other types? And so this physicist and others built a big detector. You typically, if you're looking for neutrinos, you put it in the bottom of a very deep mine. So this was done in a deep mine, I think in Sudbury, Ontario, because the rock shields out all the other particles. Only neutrinos can get down there. But his detector was looking for all 3 types of neutrinos, and it detected the right number of neutrinos when you added up all 3 types, as was leaving the sun at one type. So Mason, here's the point. He proved that neutrinos change leaving the sun and arriving at Earth, which means neutrinos are affected by time, and only objects with mass are affected by time. That's what Einstein said. Conclusion, neutrinos have mass. We don't know what the mass is, Rachel. It's ridiculously small. It's beyond our ability to measure right now, but they must have mass because they're affected by time, which means that poster behind the hovercraft that says elementary components of matter, the standard model of physics, it's wrong. Which is great. That means there's stuff out there that we don't understand or know about yet. We're going to have to add to that. And it was cool because the Canadian won a Nobel Prize. We've won 2 of the last 5 years for physics. Yeah. What do they do? First of all, neutrinos don't do much of any. They're given off. They're given off sometimes through radioactive decay. So the fusion reactions going on inside of stars give off lots and lots and lots and lots of neutrinos. There's mu neutrinos, tau neutrinos, and a third one. I want to say pi neutrinos, but I can't remember. I don't know off the top of my head. I'd have to dive into it. It's possible we don't yet know because it was only fairly recently that Nobel Prize was for showing that they change from one type to the other. So it may very well be that we still don't know the mechanism because we just recently figured out, holy smokes, they change. Who knew? They're affected by time. They must have mass. Put your pencils down, look up.